We're gonna study this polynomial function f of x being 4 times x minus 6 to the fourth times 2 minus x to the third times x plus 3 to the second power. And we're gonna answer the following series of questions about this polynomial function. So we'll start with the following 5 questions about this function. So first of all, we determine the x-intercepts of the graph of this polynomial. So we set the formula for the polynomial equals 0. Since the expression is a completely factored expression, we set each factor that contains x equals 0. So the first factor that contains x is x minus 6 to the fourth. We set it equal to 0. Then 2 minus x cubed equals 0, and then x plus 3 squared equals 0. So this first factor, x minus 6 to the fourth power being 0, is equivalent to x minus 6 being 0. So solving x minus 6 equals 0, we get x equals 6. So second factor, 2 minus x cubed equals 0, is equivalent to 2 minus x being 0. And then you get x equals 2. When you move x over. And with the third factor, x plus 3 squared is equivalent to x plus 3 being 0. So moving 3 over, we get x equals negative 3. So that's the third x-intercept. So we have x-intercepts at x equals 6, x equals 2, and x equals negative 3. So on to the second question. So we would like to find the zeros of the polynomial function and their multiplicities. And based on the multiplicities, we can determine what does the graph do at each x-intercept. So zeros are the same things as the x-intercepts. So we have the 3 zeros, since we have 3 x-intercepts. X equals 6, x equals 2, x equals negative 3. And the multiplicity comes from the power of the factor that generates a particular 0. So for x equals 6, the factor that it came from is x minus 6 to the fourth power. For x equals 2, the factor is 2 minus x cubed. For x equals negative 3, the factor is x plus 3 squared. So multiplicity is just the power that the factor has. So 0x equals 6 comes from x minus 6 to the fourth power. So it's going to have multiplicity 4, because there is fourth power on the x minus 6. The 0x equals 2 comes from 2 minus x to the third power. It's going to have multiplicity 3, because of the third power. And 0x equals negative 3 comes from x plus 3 to the second power. So multiplicity is going to be equal to 2. And then, based on the multiplicities, we can tell what happens at each of those x-intercepts. If the graph has, if the multiplicity of the 0 is an even number, like 4 or 2, the graph will only touch x-axis at that x-intercept. And if the multiplicity is an even number, like 3 or maybe 1, the graph will just cross this x-axis at that point. And so we're going to have the graph touching x-axis at x equals 6 and x equals negative 3. And the graph is going to cross x-axis at x equals 2. So if we look on the third question, what happens to the graph near each x-intercept? And what happens in between each pair of x-intercepts? So we're going to use some test points between x-intercepts to figure out what happens. So we're going to put the existing x-intercepts in sequence. So we have x equals negative 3, x equals 2, and x equals 6. So now we're going to be choosing test points in between those x-intercepts. So on the extreme left side, we have a candidate for a test point, say x equals negative 5. Between negative 3 and positive 2, there is x equals 1. Between 2 and 6, there is x equals 4. And then between, well, to the right of 6, there is x equals 7. And we're going to set up the table of values. So we're going to have the column with x values, and then we're going to have y equals f of x calculated at each of those points. So y equals f of negative 5, that will give us this expression. So just replace x with a -5 in the full original formula. And when we're done crunching the numbers, we're going to end up with this long number. But the main thing is that this huge number is a positive number. And since this number is a positive value, then we're going to be able to tell something about the graph. So at x equals 1, we calculate f of 1. We're going to have all of those numbers. So we replace x with 1 in the original formula. Get this long expression. So crunch all the numbers and we end up with 40,000. Likewise, f of 4 gives us this long expression, which calculates to -25,088. And then f of 7 calculates to this long expression, and that's -50,000. So what does the graph do? Wherever the y-coordinate is a positive number, the graph is going to be the above x-axis, somewhere above x-axis. And wherever the graph has negative y-coordinate, the graph will be below y-axis. So at the first two test points, the graph is going to be above, and at the second two test points, the graph is going to be below x-axis. So now we can start drawing the graph. So if we start on the extreme right hand, the graph should be below x-axis at x equals 7 and should stay below x-axis at x equals 4. And we know that at x equals 6, the graph should only touch x-axis. So that's exactly the behavior you expect out of the graph. Then at x equals 2, the graph should cross x-axis, so we can just draw the behavior like that. And we know that at x equals 1, the graph should be above, so that's a confirmation. And then at x equals -3, the graph only touches x-axis, so we have this bouncing off behavior. And then the graph just keeps going on. So, and at -5, we see that the graph is above x-axis, so everything checks out. So we're going to put arrows at the end of the picture. Then we have a nice and easy to use expression. So for the leading term of the polynomial, we just take the original expression, and out of each parenthesis we're going to cancel out all the lower degree terms and keep only higher degree term. So here it's going to be x minus 6, so we're going to cross out -6. There we have 2 minus x, so we're going to cross out +2. Then here we have x plus 3, so 3 is the lower term, so we cross it out. So if we collapse this expression, we have 4 times x to the 4th times -x cubed times x squared. So once we simplify this, this is going to give us the leading term. So simplifying this, we end up with -4 times x to the 9th power. So -4 times x to the 9th power should be the leading term of this polynomial. And once you have the leading term, the power of the leading term is going to be the degree of the polynomial. So leading term is -4x to the 9, so the degree is 9. Okay. And for the end behavior, once we have this picture in front of us, we can use that. So on the left hand, as x approaches -infinity, the graph goes up, so y-coordinate is going to go to +infinity. So that's the left-hand behavior. And on the right hand, the graph falls, so as x approaches +infinity, y approaches -infinity. So that's exactly the right-hand behavior. This is the second part of the series of video clips. So we're still working with the same polynomial, f of x equals 4 times x minus 6 to the 4th power times 2 minus x cubed times x plus 3 squared. We're going to answer these 3 next questions that we have on the list of questions about this polynomial. So, and to answer them, we're going to be using the answer to the question C, where we generated the schematic behavior of the polynomial. Well, so the first question is the question about the maximum number of turning points of this polynomial, and that number is equal to the degree of the polynomial minus 1. And we have calculated previously that the degree of the polynomial is 9, so 9 minus 1 is going to give us 8. So the maximum number of turning points is 8 for the graph of the polynomial. So then this next question about the y-intercept is an easy question. So y-intercept is equal to f of 0. So we replace x with 0 in the formula for the polynomial. So we end up with 4 times negative 6 to the 4th times 2 cubed times 3 squared. So this all evaluates to 373 to 48 for the y-intercept. And now we're going to sketch a somewhat more believable graph of the polynomial. So we're going to have both horizontal and vertical axes, so it's x and y. And on the x-axis we're going to label the intercepts, so then it's easier to draw the curve that represents the polynomial. So this is the curve. So it's pretty similar to what we have, but it's more stretched out in the vertical direction. And the only extra point that we can label is the y-intercept at 373 to 48. So that would be the best graph of the polynomial that we can make under the circumstances. This video is the third video in the series of video clips about this polynomial. So it continues to study the same function 4 times x minus 6 to the 4th times 2 minus x cubed times x plus 3 squared. So we're going to use this information that we got in question C to answer the following questions about inequalities. So we start by working with the first inequality, where you have the same formula for the polynomial being greater than 0. So that translates in the requirement that the graph of the polynomial is above x-axis. Since we have strictly greater than 0, that translates to the graph being above x-axis. So here is the schematic picture for the polynomial, and we can shade the places where the graph is above x-axis. And the x-intercepts -3 and +2 will be excluded points, because there the graph is exactly on x-axis. So for the answer to this first inequality, we're going to have the interval from -∞ to -3, joined with the interval from -3 to +2. Now if we switch to the second inequality, we have the inequality with the polynomial being greater or equal than 0. So the only added option is that the graph could be either above or exactly on x-axis. So here is that same picture. So I'm going to shade the places where the graph is above x-axis. And then all the x-intercepts get the filled-in points, because there the graph is exactly on the x-axis. So -3, 2, and x equals 6 will be part of the answer. So for the intervals, we're going to have the following answers. So the first interval is starting at -∞ and going all the way up to +2. And then there is a single point at 6, so we're going to have the interval from, and this is not quite right, so there is no square bracket next to -∞, so let me fix that. So there is a round parenthesis next to -∞. So we have interval from -∞ to +2, since there is one solid shaded region. Together with a single point 6. So a single point is included into curly braces. Okay, looking at the third inequality, we have the inequality with the polynomial being less than 0. So that makes the graph of the polynomial to be below x-axis. So we're going to take the same picture and we're going to shade the intervals where the graph is below x-axis. And the x-intercept is going to get punched points because we have strict inequality. So for an answer, we're going to get the interval from 2 to 6 together with the interval from 6 to infinity. Now for the last inequality, we have the non-strict inequality, the formula for the polynomial being less or equal than 0. So that says that the graph could be below or exactly on the x-axis. So taking exactly the same picture, we shade the places where the graph is below, and then fill in all the x-intercepts of the graph, so -3, 2, and 6 will be part of the solution. So for an answer, we get the interval from 2 going all the way to +∞. So we have interval from 2 to +∞, together with a single point at -3. Because that's an x-intercept, so it's also a part of the solution.